Welcome everyone to this first video that gives the introduction on differentiation. This unit of work obviously is all about calculus, and one of the great things, differentiation, one of the two branches of calculus, the other one being integration. So differentiation has a rich and beautiful history, which I'm not going to go through in this video, but just want to convince you that the applications of calculus are wide-ranging, touching just about every single part of the sciences that we can think of, and have made a huge impact in the way that we live today. The founders of calculus were Newton and Leibniz, who came up with some slightly different notations that you're going to see me use time and time again. For Newton we have fx and f-x, meaning the derivative. With Leibniz we have dy dx, the derivative of y with respect to x. So yeah, you might get either one. Let's have a look at the syllabus here. So this is called functions. 16 hours, which is a long time spent on this calculus stuff. Right, here it is, 4.1. Determine the derivative of polynomial functions from first principles. You may be familiar with that. Use the product, quotient and chain rules to differentiate functions including exponential, logarithmic and trigonometric functions. So we need to deal with all three of the derivatives of these things. And find the area under and between curves. That's some integration coming up later. So we're kind of going to leave this one till we do integration later. Then we've got determine the equation of tangents to a function, differentiate functions defined implicitly. Let me just go through, first of all, the first one, first principles. Here's y equals x squared, and I want to find out what the slope of the curve is at, let's say, x equals 1. So I want to find the slope exactly at this point right here. You can see the slope is changing all the time. So this is what calculus is all about, instantaneous rate of change. So exactly what's going on. So if this is a distance time graph, we would be talking about the speed or the velocity of the object at that exact instant of time. Okay, here's how Newton set it up. Let's take a point further on down the curve, 2. It doesn't matter how far down the curve you get. Let's draw a tangent, or sorry, a secant through those 2 points. Now you can see that the slope of that curve is not exactly the slope we're looking for. But if I make this point 2 and drag it closer and closer to 1, and keep drawing that line which we call the secant line, you can see that line will get closer and closer until it actually is the tangent at 1. Okay, here's the setup in general now. So we've got a general point x on the curve, and we've moved a little bit further along the curve, x plus h. So before I had 1 there and 2 there. At x, this is f of x, obviously, and this is f of x plus h. So this could be any curve. So what we're doing is we're going to draw this line through these 2 points and work out the gradient of that line. So if we do rise over run, you can see that this rise here, this blue line here, is just the difference between this and that. The run between x and x plus h is just going to be h. That is the gradient of that line, rise over run. Now what we want to say is the limit as h tends to 0 of that thing there. That is how Newton defined what the derivative actually is. Okay, so f dash x is that thing there. Let's apply that now to just what f of x is x squared. That's a nice easy one. So f of x is x squared. So I'm going to need f of x plus h, which is going to be x plus h squared. So if I do a bit of algebra on that now, it gives me that. Okay, so the derivative from first principles is f of x plus h minus f of x over h. And of course we want the limit of all of that as h tends to 0. Very important. Okay, so the limit as h tends to 0, okay, the top line here we can see the x squared is going to cancel out and it's going to leave me with 2hx plus h squared over h. So that's the limit as h tends to 0. You can probably see what we're going to be doing here, a bit of factorising on the top line. 2x plus h over h. So that is the limit as h tends to 0. You can clearly see that the h's are going to cancel here, and that leaves us with 2x plus h, and clearly as h tends to 0 now, this all gets closer and closer to 2x. So that means that if we start off with f of x is x squared, the derivative is always 2x. So that's doing a derivative from first principles. Some of them might get a little bit more confusing, but that's the basic idea. You should know these basic rules about doing derivatives of polynomial functions in particular, so functions of this form, x to the power of n. So that should be a really well-known rule that you should be able to do. You should be able to find the equation of a tangent to a curve and the equation of a normal curve also. You should understand about second derivatives and what they actually do. That the second derivative is the derivative of the first derivative, and how that helps us if we're talking about graphs. So the second derivative is able to help us to identify whether we are dealing with a maximum or a minimum value. So clearly at that point there the derivative is 0. The slope of the graph is 0. At that point there the slope is also 0. The value of the second derivative at this point here is negative. The value of the second derivative at this point is positive, meaning that if you have a maximum point, the second derivative is negative. If you have a minimum point, the second derivative is positive. So I kind of think opposites there. And if the second derivative is 0, it means we've got a point of inflection. Like these ones right here. Okay, 3 rules that you should be really familiar with. One is the chain rule, one is the product rule, one is the quotient rule. Let's focus on the product rule and the quotient rule. The product rule, as the name suggests, helps us to differentiate functions when they are written as a product. 2 functions multiplied together. So if we have something like this, I can identify this as the first function. I'll call that u. And this as a second function, which I'll call v. So v is root 3x minus 1. Okay, I can do the derivative of each of these functions individually, so I can say u dash is 2x, writing v as 3x minus 1 to the power of a half. I can say v dash is, I'm using the chain rule now, and this should be a revision from last year. Okay, number down the front, subtract 1 from the power there, and multiplied by the derivative of this function inside the bracket, which happens to be 3. So if I tidy v dash up a bit, I've got 3 on the top line, I've got a 2 on the bottom line, and I'll have 3x minus 1 to the power of half on the bottom line, which will look like that. Now the product rule says f dash x is u dash v plus v dash u. That is the product rule. So 2x times root 3x minus 1 plus v dash, this, times u. So we've got v dash, which is 3 over 2 root 3x minus 1 and all of that times by u, which is just x squared. So I'll just put it there on the top. There we go. There's the derivative of that function there. Now we could tidy that up by, and you may see this from time to time, answers that look different to that. So I'll show you how to do that in this case. If you make a common denominator here of 2 root 3x minus 1, and the top line now, we'd have to multiply this top line here by 2 root 3x minus 1. So doing that gives us 4x times 3x minus 1 plus 3x squared. Okay, so on the top line we've now got 12x squared minus 4x plus 3x squared. So we've got 14x squared minus 4x all over 2 root 3x minus 1. Okay, and that is the simplest way that I can write the derivative of this function. That form is actually very helpful if we now want to go on and find maximum and minimum values. Very handy to have it in that form. Okay, so I want you to now have a go at doing, in exercise 1 here, I want you to have a go at doing part B. So just let me circle that one there. Have a go at part B, 2x times 1 plus 3x squared all cubed, and write down the answer for that. Next rule that we need to know really well is called the quotient rule. The quotient rule, as the name suggests, is the rule that we use for differentiating functions when they're a quotient, like a fraction. So, it's really important to know for this one that the derivative is not just the derivative of the top line divided by the derivative of the bottom line. That does not work. We need a rule for this. So, the quotient rule looks like this, which is a little bit messy. The way that I'd write this is the derivative is equal to u dash v minus v dash u over v squared. Okay, this is just a little bit more formal to write it like this, du dx. So let's look at this example here for the quotient rule. We've got x over 2x plus 5, which looks like a really simple kind of question, but quotient rule is a way to do it. So I'm going to say the top line, like I did for the last one, u is equal to x and v is equal to 2x plus 5. Really good to set it out like this. U dash therefore is 1, v dash, the derivative there is 2. So I know that the derivative with respect to x of this function is u dash v, just using the formula, minus v dash u over v squared. Simple enough. And the top line we've got 2x plus 5 minus 2x, so we just end up with 5 over 2x plus 5 squared. Okay, I could then ask a question like, what are the stationary values of this function here? When is the derivative equal to 0? And if you look at that carefully, you will work out pretty quickly that this is never 0. This fraction here is only 0 when the top line is 0, which it never is. So, in fact, this function here has no turning points, no stationary values. Okay?